Okay, are there any questions? I have a quiz ready for you, but I'll give it to you towards the last half an hour or so. Why are you laughing? Do you have comments? Or? Yeah, towards the last half an hour, 40 minutes, whatever. I want to finish this boundary layer in fluids, and then I'll give you the quiz. The next lecture, next week I won't be here, so there will be no classes for 2 days, and then I come back the week after that. We'll continue with heat transfer boundary layers and mass transfer boundary layers and stuff like that. So I don't think it should take more than half an hour. I think it should be fine. All right. In the last lecture, we looked at the Blasius solution. So we saw boundary layer theory as a theory that bridges the gap between potential flow and creeping flow, and it's able to track the sharp changes in velocity profile over a small distance near solid objects. That's where the boundary layers typically occur. And we could derive the equation governing such phenomena from the Navier-Stokes equation by doing proper scale analysis, which is the Prandtl boundary layer equations that you should be able to derive. And then we saw that it is parabolic in nature. So in that process, we went through the classification of partial differential equations to understand what we mean by parabolic, elliptic, or hyperbolic. And we defined other metrics for deciding how thick a boundary layer is. The boundary layer thickness, which is simply the distance over which the velocity reaches the 99% of the free stream velocity. And then the displacement thickness, which is defined as the thickness by which the fluid has been displaced with a uniform velocity and zero velocity near the plate. And momentum deficit is the same idea. What is the deficit in momentum between the inlet and outlet? And that is caused by the drag on the plate. And we are going to use these two definitions today in developing something called an integral method. But the differential method, the Prandtl boundary layer equation, was solved by Blasius. And in the last lecture, we saw that by introducing a similarity transformation, we can convert the Prandtl boundary layer equation into an ordinary differential equation, a third order nonlinear ordinary differential equation, subject to the three boundary conditions, which come from the fact that the plate is no slip and there is impenetrability, and as you go far away, it approaches the free stream velocity, okay, which comes from here. And we saw that there is no analytical solution to the Blasius equation, but there is a numerical solution which is typically given in the form of a table, and we need to understand how to interpret the table. And then today we will look at how good is the solution compared to experimental results. In a sense, how valid or how realistic is this concept of a boundary layer. Okay? So the first thing that we want to do is measure the shear stress, okay, at the wall. So remember, we are still solving the boundary layer over a flat plate, and we want to calculate at a given point what is the shear stress at the wall. Okay, and by definition, that shear stress expression is given by mu times dv1 dx2, the velocity gradient of v1 in the x2 direction. So this is x1 and that is x2, and that is your boundary layer. Okay, and the velocity field is like this, and we need the slope of the velocity field at the plate. And so that is the definition for what a shear stress is in terms of the rate of shear rate components. But we know that V1 is equal to d psi dx2. Our solutions are all in terms of the stream function. Okay, so we make that substitution and express the shear stress in terms of the derivative. So it becomes the second derivative of psi with respect to x2 squared. But we have already obtained the solution. We already know how we define the stream function psi as square root of, I guess it's u nu x2 times f of eta. So the stream function is basically this unknown function f, which is what numerically has been solved. So we know f, f prime, and f double prime in this table, f, f prime, and f double prime, obtained as a function of eta. So this is your independent variable eta, going from 0 all the way to infinity. But infinity is just a concept. So in this case, you find that numerically when you integrate, if you reach eta of 8, you already have reached the edge of the boundary layer. How do I know from this table? I made the statement that if I reach the eta value of about 8.8 in this table, said that is the edge of the boundary layer. It's as if I've gone to infinity. How can I, what in the table makes me state that? Remember, this is f prime, this is f double prime. Now, what is f prime? F prime is v1 over u. Okay, so if that number approaches 1, that means v1 has approached u. Okay, so I can make that claim by looking at the second column. So I'm already at the edge of the boundary layer. Depending on how you define, these are all outside of the boundary layer. If I'm just looking for 0.990, that is 99%, is what I defined. Okay, so we can say that the boundary layer edge is somewhere there if you accept 99% as the limit. Okay, so you don't need to integrate up to infinity, but once you go far enough, you can stop. Now the third column gives you f double prime. Now what information does it contain? So physically, f contains information about the string function, because psi is equal to square root of nu u x1 times f, as I showed here. So the f contains information about psi, f prime contains information about velocity v1, and f double prime contains information about the shear stress, okay, as a function of eta. So what I need to do is use the definition for psi in here and take the derivative, partial derivative of the second derivative of that function, and you will get f double prime evaluated at 0, because it is x2 at x2 equal to 0. That turns out to be eta equal to 0. So the question now is, how do I calculate the shear stress from this formula and the table? All I need to do is, well, these are all functions that I know. U is a velocity I know, viscosity I know. X1 is spatial position at various locations. But this is going to be a constant number. And that number is the first number in the third column. At this number, 0.33206. Okay, that is f double prime at 0. This is f double prime at 0. So pick that number and put it back into this expression. Replace this by 0.33322. Okay, that is coming from a solution. So from a solution, even though we have the complete velocity profile, we are primarily interested in two macroscopic quantities. One is, at what value of eta does it reach 99%? That happens when eta equal to 5. From that, you can discover what is the constant in the expression that we had. Delta over L is equal to 1 over square root of REL. Now we know that we can replace this by 5 divided by that. The second thing is, what is the shear stress, or what is the friction factor? Okay, so the friction factor, here it's an unfortunate choice of symbols, but this function is not the same as this. Okay, this is an unknown function, but f here is the friction factor. This is the friction factor. And it is defined typically as tau divided by 1/2 rho u squared. Same as drag coefficient. Maybe I should have called it as drag coefficient. Okay, and then substitute for tau that we obtained from the previous step. That is 2f double prime 0. And then you get this square root of mu square u cube rho and all this. And now substitute for f double prime as 0.332. So you get f as a function of x1. So the subscript here, x1, typically indicates that this friction factor is a function of the position where you are, because x1 appears in here. Okay? And the Reynolds number based on x1 appears there. So that is called a local friction factor. The friction factor at a particular point. It's important that you understand the implication of this. So the friction factor at this point is going to be different from this point. It's going to be different from this point. It's going to change. Okay, how does it change? It changes as 1 over square root of Reynolds number based on that distance x1. So what happens to friction factor as x1 increases? Decreases. Okay. What does that mean? Sorry? What does that mean? That the friction factor at every point is different. This is the first time we are coming across, well, I guess we did that too also in a sphere, stress on a sphere, but we never really discussed this. So maybe we'll take this time to understand what does it mean. How can you measure that local shear stress or local friction factor? It simply means that at every point the force exerted by the fluid on the plate is decreasing. So if you take a point farther downstream, the force exerted by the fluid locally on that point is going to be smaller than the force exerted by the fluid at near the inlet. But what we can easily measure is the total force. Okay, I can easily put this on a spring-mounted device where I can, by looking at the extension of the spring, I can find out what is the net force exerted. That's where we integrate, which is what we did for a sphere also. We integrated the force around the sphere and then we get the net drag. And that we can do in this case by integrating an average friction factor or an average drag coefficient, which is nothing but integral from 0 to L of the local friction factor multiplied by dx1. dx1 is the differential length divided by the total length L. And when you do that, you will get, instead of 0.664, you'll get 1.328 divided by REL. Now, what is the difference between this expression and this expression? The first expression is distance x1 measured from the leading edge, and that gives you, when you use that distance, it gives you the local stress, the local friction coefficient. But when you use the coefficient of 1.328 in the same expression, again it's still the same length. So this one will give you the total force exerted from 0 to that point L, wherever that L is. Do you understand that?
So, like the local Reynolds number is larger than 2000.
Good question. We are going to discuss that again, a little later. But the 2000 number is only valid for pipe flow and circular pipe flow. Okay, so even if you have a rectangular flow, rectangular duct, the transition occurs at a critical Reynolds number, but it is not 2100. It may be a different number. Okay, now, yeah, go ahead.
You said the first one is for the local friction, and that one, the second one is for
the total friction up to that point.
Okay, so even at for the first one, x equals L, that's still a local.
Right. So the factor that determines is whether you are using 0.664 or 1.328. So the length remains the same. Suppose I have a plate and I say I measure up to 10 centimeters. Okay. So when I put x1 equals 10 centimeters in the Reynolds number expression and I use it in this formula with 0.664, what am I getting back? I'm getting back the local stress, the local friction factor at 10 centimeters. But if I take the same 10 centimeters and treat it as L and put it in this with 1.328, then I'm getting the total force exerted from 0 to 10 centimeters. Okay, so that's the difference between a local coefficient and an average total coefficient. Okay, now how can I measure, for example, people have measured the variation of the local shear stress, and I'll show you some of the experimental data later on. How can you measure that? Can you think of a thought experiment that you can do to measure what the shear stress is on a plate? Of course, if it is a steel plate, you cannot do it because it's not going to erode or melt away, or you need to find a material that will respond to the local shear stress. Okay, so if for example, if you take a plate made of a naphthalene ball that sublimes, for example, okay, and it sublimes based on the local velocity gradient, then you can actually, by measuring the changes in the thickness of the plate over a period of time, you can say what is the local coefficient. And people have done very careful experiment to measure the variation of the local coefficient with distance, and of course the average one also, the total. And they agree quite well with the theory predicted from this equation. Now, the question about the transition, when does it become turbulent? Does this boundary layer remain laminar for any length? Because the length is the one that determines what the Reynolds number is. And what happens is, in real life, about Reynolds number 2 times 10 to the 5, the laminar boundary layer will break down and it will start becoming turbulent flow. Okay? What that means is, if I put a streamline of a red dye or a smoke, the smoke will basically translate as a uniform stream without breaking up. But the moment it reaches this, it's going to diffuse much more widely. The boundary layer thickness becomes completely different. So where that happens is roughly 2 times 10 to the 5, based on the length of the plate. So there is a certain length of the plate where you will hit that Reynolds number. And beyond that length, if the length of the plate is larger than that, the laminar boundary layer will become turbulent. And that one can understand only by, again, stability argument, stability analysis. So it's not 2100, but it's a much larger number. Any other questions? Okay. Here is the table, and we saw how to use the table. But let me give you some results. This is the friction coefficient. Luckily, in this one, they did use SCF for the friction coefficient, which is defined as tau divided by 1/2 rho infinity square. And here you see experimentally direct skin friction measurement. Direct measurement means they're measuring locally what is the friction coefficient at certain distances. Okay, and the theory is the solid line. And you find that the agreement is excellent for the laminar one. But it does become turbulent at a Reynolds number of about 10 to the 5, 2 times 10 to the 5. Beyond this, this graph can extend because it's a stability problem. Sometimes you may be able to realize laminar flow at an even higher Reynolds number if you don't have any disturbances. If you have any disturbances, the disturbances can grow due to instability, then the transition can occur. So the transition actually occurs over a range of Reynolds number, starting at 2 times 10 to the 5. If it is below 2 times 10 to the 5, you will always have laminar flow. Above that, you could have a turbulent flow as well. Turbulent boundary layer theory, we cannot really analyze from the Navier-Stokes equation. Now, this is a proof of the velocity measurement inside the boundary layer. Okay? So what they have done here is measure this curve at various locations. Okay? And remember, this is a self-similar solution because we have used similarity transformation. So if I have this curve, I should be able to stretch that at a certain distance away from there to produce this curve also. That is, all the velocity field at various locations of x1 will collapse into a single curve. And that curve is f as a function of eta, and the x-axis is your eta, okay, which is what we call as x2, square root of u over mu x1. Okay, so that single variable collapses all these curves into a single curve. And there you see the data points are from experiments. Solid line is from the Blasius solution. How would you generate such a graph? Question, yeah.
Is that still true even after it goes beyond?
No, it's valid only in the laminar regime because the Blasius solution, Prandtl boundary layer equations are all valid only in the laminar regime. Okay, so this is valid only when Reynolds number is less than 2 times 10 to the 5. How would you generate this graph? If I give you the table, how would you generate this graph? It's nothing but the plot of the first column with the third column. First column against the third column. Third column is the y-axis. First column is your x-axis. Okay. The other thing that you should be able to do in a quiz or a final exam would be, given that table, if I ask you to construct this graph, that is, plot the velocity profile at a distance of x equals 1 centimeter. How would you do that? Okay. So you basically need to use this graph and fix x1 as 10 centimeters and put in all the other numbers that are given, the free stream velocity, kinematic viscosity, and then various values of eta will give you various values of x2, that is the distance from the plate to the edge of the boundary layer. And so put in various values of x2, find out what eta is, and then go and read that value, and that gives you what v1 is. So you can generate this graph. So you change your x1 to a different position, put in that new value, the same graph will give you the velocity profile in that new location. Okay? Any questions? Okay. Yeah, we already talked about this, that how do I define the boundary edge of the boundary layer thickness by simply asking the question, for what value of eta does f prime become 0.99? F prime is the ratio of v1 over u. Okay, f prime is the same as v1 over u. At what time, what position of eta does that become 0.99? And you find that that is equal to 5 from the table. Okay. The next one, I have given a big section as reading assignment, and whenever I say read this, even I did that in potential flow, I expect you to be familiar with that section in terms of the final exam. Okay, so this is generally an extension of the Blasius solution for geometries that are different from flat plate. So flat plate is one where we have studied, okay, something like this. The approach velocity is parallel to the plate. What happens if the approach velocity is, the boundary layer is over a geometry like this, a wedge that we have already studied from potential flow. So in that case, if the velocity, approach velocity is still like this, you will have a boundary layer that develops like that. Okay, and the Faulkner scan solutions basically develop the Blasius. The boundary layer equation is still the same, but now you will not have u as equal to a constant. What is u? The u here is constant, but the u here is a function of x1, and this is x1. Okay, so there is a pressure distribution at the edge of the boundary layer. For flat plate, that was 0. Now you will have a non-zero pressure distribution, and it basically takes you through the same mathematics that will allow you to construct a similarity transformation and construct a solution for a whole class of geometries like that, sectors of various angles, alpha. You can even have alpha is 180, then you will have an impinging stream, a boundary layer development near that, the stagnation flow. So the mathematics is basically the same. Okay, so I want you to look at that and be prepared for the final exam. What I want to do in the next, I'm going to give myself half an hour to finish this so that we can move to the quiz. Develop something called the one Karman integral method. One Karman is another famous fluid dynamicist, and he developed this because he realized that the Blasius solution is a very challenging task to solve because you have a nonlinear ordinary differential equation. So he was asking the question, can I solve the Prandtl boundary layer equation at least in an approximate way? Okay, not in an exact way as Blasius did, but in an approximate way. And he used this idea of an integral method. The basic idea is the following. If I have a boundary layer with x1 and x2, I'm going to take a control volume and I'm going to look at the momentum that is coming in at the entrance. So I'm going to integrate across the total momentum. I'm going to take the momentum equation and integrate from 0 to infinity in the x2 direction. Okay, and that momentum I'm going to balance against at the edge. So I'm going to do an integration of the x1 momentum equation, use the continuity equation in there, and see whether I can develop a simpler integral equation that will tell me how the boundary layer thickness changes with x1, but it will not tell me what the velocity profile is. I will not be able to predict what the velocity profile is because I'm integrating, I'm losing information. Okay, I will not be able to predict what the velocity profile is. But if I put in a known velocity profile, I should be able to solve for what the boundary layer thickness is. I should be able to solve for what the shear stress at the wall is, which is based on the gradient. Okay, so that is the main idea. using an integration of the momentum equation in the x2 direction and foregoing the ability to predict the velocity profile, but still retain the ability to predict the boundary layer thickness and the shear stress. So we're going to use these notions. This is why we introduced the displacement thickness and the momentum thickness, because these are given in the form of integrals. Okay, in fact, the second one is the momentum deficit, integral of the momentum deficit. Okay, so we're going to use this both delta star and theta. But our starting point is going to be the same Prandtl boundary layer equation. So here you have the continuity equation and the x1 or the u momentum equation. And he did it not just for the flat plate, but more general case. How do you know whether you're doing it for a flat plate or the more general case? You know it by looking at this term. If I drop this term, I'm restricting it to the flat plate, because for a flat plate u is a constant, that's 0. If not, then I'm handling the Faulkner-Scan type of boundary layer past sectors as well. So conceptually, let's make sure that we understand it. I'm going to take this equation and do an integration between 0 and infinity in the y direction, every term, term by term. So when I do the integral, I'm losing information about the velocity variation in the x2 direction or the y direction. Okay. Now the mathematics is a little bit tricky, and in Burstall and Lightfoot, I think they do talk about the integral method, but then they just give you the final result, I think. So the steps are the following. I'm going to add and subtract a common term, lowercase u, which is the x1 component velocity, multiplied by du dx. I can do that without changing the equation. So here is my subtraction, here is my addition of the same term. Okay, and then for every other term in the momentum equation, I have switched the sign to minus, 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 and minus. Okay, I flip the sign everywhere, and then I simply add and subtract. So this is minus and this is plus. Okay, and then what I've done is I have combined the two terms that I have identified in yellow. That is u times du dx, which is the same as the term on the right hand side, minus u times du dx. When that term goes to, when minus u du dx goes to the left hand side, it becomes u du dx. And then I have minus u du dx. So I combine this as u minus u. Capital U is the potential flow at the edge of the boundary layer. Lowercase u is the velocity inside the boundary layer. Okay, so the LO terms in the previous equation have been combined into this, and then the two terms that you see in purple have also been combined. So this is the same as this term. Okay, so I have taken u as the common factor out, and then d dx of capital U minus u. Okay, that is capital U minus lowercase u. So I've combined those two. And on the right hand side, I still keep the term, the viscous term as it is, minus mu times d square u dy square. What have I done with this term? Is that valid? Is that legitimate? I have basically taken this term and replaced it by this, and I'm claiming that they are the same, right? When will they be the same? If u is not a function of y, what happens? When you take the partial derivative of that, it will become 0, right? So if u is not a function of y, that will be true. But is that correct? Is u is not a function of y? Of course it is not a function of y, because u is a function only of x1. x1 is this direction. U is the velocity profile at the edge of the boundary layer. This comes from potential flow. So it is not a function of x2. It doesn't change with x2. So I can put that inside, because when I take the derivative, it will be 0. You can ask, why am I doing that? But you can see a pattern there. What pattern do you see? U minus u. In every term, I have introduced that u minus u. Okay, so that's a kind of a momentum deficit. Okay, and any questions on that manipulations? The next step is I'm going to do use the definition of the displacement thickness. So I'm getting all this in terms of u minus u, and so I'm going to use the definition of the displacement thickness, and I'm going to take this. Now I'm working term by term, so I should tell you what term I'm working on. First thing is I'm working on this term, okay, u minus u times du dx. I'm going to integrate between 0 to infinity every term dy, but I'm picking term by term to show you what the manipulation is. So let me work with the first term. This is the first term. So integral between 0 to h is at the edge of the boundary layer, capital U minus u, du dx dy. But du dx is not a function of y. Why? Because u is not a function of y. So I can take this outside of the integral. That's what I do. Then whatever is left, which is integral of 0 to h u minus u dy, is by definition the displacement thickness, u times delta star. Okay, so the first term has been reduced to in terms of the displacement thickness, du dx times u. Remember, u is a known function. How is it known? By solving the potential flow at the edge of the boundary layer. Okay, so that means whilst getting u, you can use the potential flow theory. Forget about the boundary layer. Take whatever shape of object that you have, solve for the potential flow, and evaluate it on the plate, and that is going to be on the wall, and that is going to be your u, which will be changing with the wall length, along the arc length of the wall. The last term, okay, I take the last term from here, minus mu times d square u dy squared. Okay, and I write this as d dy of du dy because it's a second derivative. The reason I do that is now I can cancel the dy, and then I have integral of the derivative, which will be the same function, integral of derivative of this. Okay, so that is going to be, if I have to write an intermediate step, this is going to be the same as minus mu over rho du dy evaluated between 0 and h. Okay, but when you evaluate it at h, what happens to the derivative du dy? 0, because it's a potential flow. There is no shear stress and potential flow at the edge of the boundary layer. But at the bottom limit, when the plate is at 0, then that is your shear stress at the wall. Okay, when combined it with mu. When you combine it with mu, that becomes tau 0. So the right hand side has been integrated across the boundary layer, and that gives you the expression for the shear stress at the wall. Okay, then the third term. What is the third term? We're talking about this term. Okay, u times d dy of capital U minus u. We're going to integrate that. Okay, so here you have v times, I guess it's v, right? Did I say u? It's v. It's v times d dy of u minus u. Okay, so v times d dy of u minus u dy. Now I need to do this by integration by parts because I have a product of two terms, v and d dy of this. Okay, that is, if you remember the integration by parts, you call this as f, this one is g, then by parts will be fg and g times df dy. Okay, so you need to remember, recall the integration by parts. So the first part simply becomes v times u minus u between the limits of 0 and h. What would that be? That will be 0. Why? When you evaluate it at 0, the velocity at the plate is 0. When you evaluate it at h, this velocity, capital U, becomes small u. Okay, the difference becomes 0. Okay, so this entire term would drop out. And then the second one you have is the derivative of v with respect to y multiplied by the function itself, which is your integration by parts. Okay, so that is then replaced by, that is equal to 0 to h. What did we do here? We took the continuity equation. Remember, we are working with the momentum equation, but we still have the continuity equation, du dx plus dv dy equal to 0. So I take this dv dy and replace it by minus du dx. And that's why I have the sign minus becoming plus, and this becomes du dx. Instead of dv dy, it becomes du dx. What have I achieved so far? I've gotten rid of v from my equation. So I'm getting everything in terms of u, the lowercase u, and the deficit, the difference between capital U and small u. Yeah?
Yeah, we said when y commute 0 at the place, the vertical velocity v is 0.
Yeah.
But so if it's not a flat plate, it's not a curve.
Yeah. It will still be true, because as long as the plate is impenetrable, that means there is no liquid seeping through the plate. That condition will always be true, because it is impenetrability condition.
But this will be it's not perpendicular to the surface.
That's a good question. Okay. Very perceptive question. You need to look at the Faulkner-Scan's solutions. When you're developing that, what you do is, if the plate is inclined like this, you will set up a local coordinate. You will call this as x1, you will call that as x2. So u and v are still velocities that are parallel to and perpendicular to the plate. Okay, and that velocity would be 0. Now, if you have, what happens, this has also been done. If you have a bluff object like this, a curved object, okay, and the flow is coming like this, and you have a boundary layer that is developing like that, then you need to set up a local coordinate along the curve. This is where ideas from curvilinear coordinates will come in handy. So you'll set up a coordinate that is going along the contour of the shape of the object, and one that is perpendicular to that. And so you will still have a perpendicular velocity as being 0 in all these generalizations. The only case when v will not be 0, in which case you have to retain the term as you do the analysis further, would be when you have a porous plate, when you have liquid being injected or withdrawn through that. Okay. Any other questions? Okay. So yeah, so as I said, we have used this dv dy equals minus du dx, and so the third term becomes that. Now we plug all the manipulations that we have done. On the right hand side, we integrated, we said it is equal to tau 0 over rho. On the left hand side, we integrated the first term, expressed it in terms of deficit thickness, and we integrated the third term, and this is what we got. We keep the second term as it is. Okay. Now we combine the second and the third term. Okay, so 0 to h. Everything else has been replaced by the algebraic expression, but the second and third term remain within the integral. Okay, so I'm going to regroup them by simply writing it as combining that. It's a mathematics question. What have I done? What manipulation have I done? Chain rule. So basically, if you apply the chain rule on this term, you'll get u times d dx of u minus u, which is the first term, multiplied plus u minus u times du dx, which is the second term. So it's a way of combining the two terms using the chain rule idea to express it as a single term. Okay. The next thing I've done is I've taken, because I'm integrating with respect to y, I'm switching the order of differentiation and integration and realizing that everything changes only in the x direction. So I have replaced the partial derivative by the total derivative, because that expression is not a function of y. So I can take that out, and when I do this, the meaning, the interpretation for this is it is a momentum deficit, u square theta. This integral is nothing but u square theta, this entire integral. So all I have is d dx of u square theta. And this is called the von Karman integral equation. It doesn't have the ability to predict the velocity profile, but if you give it a velocity profile, it will predict what the shear stress is. You can calculate what the shear stress is. Okay? Any questions on that? And this is valid not just for flat plate, but for even plates that are at an angle with respect to the free stream velocity. Now, as an example and illustration, let's take a flat plate where u is constant, so this term drops out. du dx is 0. Then the momentum equation, the integral momentum equation, simplifies to this. Okay? So it's an ordinary differential equation that I need to solve to find the boundary layer thickness theta and the shear stress at the wall tau 0. How do I do that? So I'm just going back to my notation because this is the momentum deficit thickness, which has a definition. So I'm going to write that as using the definition back. I'm going to write that as d dx of integral u minus capital U over minus u, which is the momentum deficit, dy equals this. So this is exactly the same equation, one Karman integral. But I need to put into this a velocity field within the boundary layer. Of course, u I know, that comes from the edge of the boundary layer. Okay, but in this case, u is a constant for flat plate. But I need to put in an expression for the boundary. U is, remember, u is the velocity inside that boundary layer. This is u. So I need to put a profile. I need to put a function that captures what u is. And if I do that, then I can integrate that out. And I can then get a differential equation for the boundary layer thickness that I can solve. And this is illustrated in Berstewart and Lightfoot and a number of other books. You will find use of different expressions. So this is not a prediction. This is an assumption. What do we assume? We assume that the velocity profile that I have sketched here, that velocity profile is given by this expression, a polynomial, a cubic polynomial. You can choose a quadratic polynomial. You can choose a straight line. For example, you can say this boundary layer velocity is something like this. It will not be true, but what you will find is surprisingly that the result is not that bad, even if you assume that this u is a linear function. You should be able to do this in an exam. If I give you a linear, quadratic, cubic, or sine wave, or whatever, okay, that is, this would be your starting point. I give you a velocity profile, then carry out the integration and get the thickness and the shear stress at the wall. So in this case, I have A, B, C, D as unknown constants for a profile that I'm proposing. So I'm saying that the profile is going to be cubic. What are the best values for A, B, C, and D? I find that by imposing a certain set of realistic boundary conditions. One of the conditions is the velocity is 0 and d square u dy square is 0. Does that make sense at the wall? So I'm making, remember, I have 4 constants here that I need to find out. I made a proposal for a velocity profile. That proposal has 4 unknown constants. It's a cubic polynomial. I need to find these constants in such a way that the velocity profile will satisfy the boundary conditions. Okay, and I'm saying one of the boundary conditions is we have already talked about, u is equal to 0, no slip condition. The other one is u equals capital U at the edge of the boundary layer. That's a free stream condition. And it is these 2 conditions I want you to think about, because it is based on the physics. It's based on the application of the physics. So what am I saying when I say, for example, du dy equal to 0 at y equal to delta? The edge of the boundary layer, there is no velocity gradient. There is no shear stress because it's a potential flow from that point on. So this condition simply says no shear at edge of boundary layer. What does this condition tell you? How did I get that one? That's a little bit more tricky because you need to look at the equation, the Prandtl boundary layer equation, u du dx plus v du dy equals nu d square u dy square. That is the Prandtl boundary layer equation. But if I evaluate that at the plate, what happens? At the plate is u is 0. At the plate v is 0. Right? So the d square u dy square must also be 0 at the plate. Du dy is not 0. There is a shear stress. Okay? But the second derivative is equal to 0. And that's what we are saying here. So we are applying the boundary condition from the equation itself by applying it at the wall. When you put these 4 conditions and solve for the 4 unknown constants, you will get the velocity profile to be this. Okay, 3 over 2 y over delta minus 1/2 y over delta cube. Now you take that velocity profile, put it in here, and do this integration. When you do the integration, you get the integral, which is the left-hand side of the integral momentum equation, as this expression, 39 over 280 u square over delta. Now, depending on what form of polynomial that you put in, if you put a quadratic, this number would be different. but you will always get a u squared delta out of that. So the constant depends on what kind of velocity profile you put, and there is an exact value for the constant, which we can get from Blassius equation if we want. Okay, but in an approximate way, we put a proposal for the velocity profile, we carry out the integration, and we get a constant. That constant is depending on what profile we assume. Similarly, the definition for tau 0 is nu times dy. Nu is kinematic viscosity, mu over rho. So divided by rho on the left-hand side. So take the same velocity profile, plug it in here, and take the derivative, and you will get the right-hand side of the momentum equation, the integral momentum equation. So now you equate these two. Okay, 39 over 280 u squared delta, which is this term, left-hand side, and put this on the right-hand side, because that is the integral momentum equation. Now you have a differential equation for the boundary layer thickness. So you integrate that, and you will get this expression. In preparation for the final exam, you should be able to carry out, this is a simple problem, okay, you should be able to do. I'll give you the Prandtl boundary layer equations, the one common integral equation, then a velocity profile, and say obtain an expression for the boundary layer thickness, and do the same thing for friction factor. Okay, and the friction factor becomes 0.646. Now these constants, 4.64 and 0.646, what are they for the exact Blassius solution? For the Blassius solution, this is almost 5, and this is 332,664, I think. This was 0.664 instead of 646. So the error that you introduce is a lot less by assuming some sort of a velocity profile, and you can still get the friction factor instead of having to go through what Blassius did, which is use the Rangakata method to carry out the integration. Days of calculation in the 1930s. Nowadays, of course, you can do it in a matter of minutes with computers. Any questions? We talked about this transition, right? So this is where the transition will begin, and the boundary layer thickness will begin to grow at a much faster rate than in the laminar flow, and that occurs around 2 times 10 to the 5. And the other concept that we need to look at is separation of the boundary layers. So in a flat plate, the boundary layer does not separate. But we know, as you have done in your current assignment, if I have a sphere, when the initial effect becomes important, the flow separates at the back. Okay, so there is a separation point. Will the boundary layer also separate? And the answer is yes, because what you will have, in fact, is a boundary layer that goes like this, and then it separates there. So what happens at the separation point to the flow field? And once again, we do the same sort of an analysis that we just did. U du dx, this is the Prandtl boundary layer equation. V du dy equals dp dx plus nu times d square u dy square. That is the general Prandtl boundary layer equation. But on this curved wall, setting up a local coordinate system, watch here, x and y are perpendicular to each other. But x is always going along the length of the curve. X is measured along the length of the curve. Okay? So on that plate, this u and d will be 0. No slip, impenetrability. So what you're left with is dp dx equals minus d square u dy square. Okay? And that is this equation. So what that tells us is, when the separation occurs, the dp dx, the pressure gradient, changes sign. It is less negative at one point and it is positive at another point. Does that make sense? Why is the pressure gradient negative here? Because the flow is in this direction. If there is friction, there has to be pressure decrease. Right? So the pressure gradient is negative, but once the separation occurs, the pressure gradient actually becomes positive. And that means the velocity field, the second derivative, must be 0 at the point where the pressure gradient is exactly 0. So it develops an inflection point. And that's how you can detect where the separation point is. Okay? So this is a point where the second derivative of the velocity is 0. So the velocity profile develops an inflection point, And beyond that, the velocity profile will actually have a negative velocity. Okay, and that is shown in the contour in the last figure. So this is how this would be the velocity profile before separation. At the point of separation, you get an inflection point, and beyond that, you will have a negative velocity and then a positive velocity. Okay, so the streamline will just go like this, and zero streamline will be this. There is a separation line. And any other streamline will actually come into this and then turn back. So this is the separation zone. So whenever you have curved objects, if the inertia is large, the boundary layer can separate, and these are some of the characteristic features of the separation point. Okay, so maybe we'll stop there because it's already 4:30. The last figure simply shows how does the boundary layer look for flow past a circular cylinder. Let me just start with this one. Try to answer all the questions as much as you know. Okay? You don't have to complete. I'm just throwing your mind of what you have learned so far. And this will not count, so it's a lot of points except the 5% for. Yeah, it's a closed book, right? It's a closed book, yes. Yeah, you guys need to use the paper. Yeah. Did everybody get a copy? So till about 5 o'clock.